Awesome, thank you. So yeah, let's dive right into this session, and it's going to be on disinfection and chlorination. So the biggest purpose of chlorination is, of course, the disinfection aspect of it. We want to inactivate and or kill as many or pathogenic organisms that we find in the water, right? But some other aspects of chlorination and why it's useful is also that its unique properties make it a good candidate use for controlling taste and odor, algae, and also slime. It is also very useful because it leaves a measurable residual out in the distribution system, which can continue inactivating organisms, right? And it one of the uses as well is the control of zebra mussels. So zebra mussels are indigenous to the fresh waters of Europe and were brought via commercial trade to the Great Lakes around the 1980s, and they adopted really rapidly to the Great Lakes and posed problems for water treatment plants. They attached themselves to intake structures, to pipelines and other parts and components of the water treatment plant. And one way to control them is through adding chlorine. Um, Another purpose and a possible use for chlorine is that it can oxidize metals. This is why we see in a lot of the smaller systems that say have some arsenic filters, they apply chlorine to be used as an oxidant to drop that arsenic out of solution, solidify it, and then kind of filter it out through their filtration membranes, right? So it can have multiple purpose other than the disinfection aspect of it. But as far as disinfection, again, we want to deactivate or kill as many of those pathogenic organisms, such as typhoid fever, dysentery, infectious hepatitis, cholera, and there's many more. Another thing is that disinfection is not sterilization. To sterilize something would cost a lot of money. Sterilization is the destruction of all living organisms or all organisms, right? We are disinfecting to a certain level, a certain degree, but chlorination is the most widely used disinfectant chemical for a variety of reasons, and it's used worldwide. It is easily obtained, it's effective, relatively inexpensive. Not too sure after COVID-19, the price on some chlorination chemicals have gone up. So, it's relatively inexpensive. It's reliable, and again, it leaves a measurable residual out in the distribution system that can be measured and can continue in activating organisms. But like with every good thing, however, chlorine also forms trihalomethanes and haloacetic acids, which may contribute to an increased risk of cancer. And some alternatives to disinfection, alternative chemicals or methods are chlorine dioxide, chloramines, if you're a chloraminating system, which we'll talk about further in the presentation, some ozone, some UV rays, right? With all these alternatives, however, they don't meet all of the 5 criteria listed above. Some may be more expensive than others may be less reliable. So chlorine still continues to be one of the most widely used disinfectant chemicals worldwide. So with disinfection, the main purpose again is to inactivate as many of those living organisms, right, as possible from the drinking water supply. And it still continues to be it still continues to be one of the biggest influences for applying chlorine to a system. So from this graph on the y-axis, we see the rates per 100,000 or death rates per 100,000 population. On the x-axis, we see the dates from 1900 to 1960. So, and this is the death rates due to typhoid fever from in the United States. We can see that around 1908, with the introduction of chlorination, that's kind of where it started beginning. You start seeing a drastic decline in death rates as the years went by, And as more and more cities adopted chlorination as an acceptable technique, all the way up, kind of peaking out into the late 1940s, right? And this is only death rates due to typhoid fever, right? There's cholera, there's many other pathogenic organisms that we don't see, but it's hard to imagine that people would die from drinking their public water, and it's of course really reduced today. Now, here are some definitions that we're going to be going through and they're going to be coming up in the presentation. So let's go through them quickly. Available chlorine is going to refer to the oxidizing power of the chlorine compound, and that usually comes from your product data sheet. We have free available chlorine. That refers to the concentrations of the hypochlorous acid and hypochlorite ion in the water. The chlorine applied is the amount of chlorine added to the water. The total chlorine residual, that's the amount of chlorine remaining in the free and combined form. The free chlorine residual is the amount of chlorine that has not reacted with other compounds found in the water, right? And then going back to the total and how that relates, the combined chlorine residual is the amount of chlorine that has reacted with natural ammonia, mostly some other organic material, some other organic nitrogen containing compounds in the water to form chloramines, which is a form of a disinfectant, right? And we'll dive a little deeper into that. The chlorine demand, which is the difference between the chlorine applied and the chlorine residual, usually the amount of chlorine that has reacted with or is lost to other substances in water and is not found as free or combined chlorine. So as we will see further on from the graph, there will be in many water supplies a chlorine demand that must be met before a residual can be observed, right? So let's talk a little bit about the properties of chlorine. Chlorine has an atomic weight of 35.5 and a molecular weight in the gaseous form of 71.0. So chlorine gas, referred to as the elemental chlorine. Chlorine gas does not exist naturally. It must be manufactured via electrolysis. And chlorine itself is not explosive or flammable, but still it is very dangerous to human life. If you breathe this, your lungs are in, really big danger. So concentrations greater than 0.3 parts per million in air can be detected by smell and dangerous to life or human health at 10 parts per million in air. Again, any quantity that you're breathing of chlorine is still not good. So dry gas itself is not corrosive, but it can be very corrosive in moist environments. So what happens, and as you start looking at some of these systems that apply chlorine through the variety of different chemicals that are used at the application site, if you start seeing a drip, you will also start observing with respect to time, you'll start seeing that there will be corrosion around that general area in the pipes. Well, what happens is when chlorine gas reacts with the moisture on those pipes, it forms hydrochloric acid and hypochlorous acid, which is very corrosive, and why you start seeing some of that corrosion occur. Some further properties of chlorine. There are three basic types of applications, chemicals for chlorine. One is the gaseous chemical form of chlorine. It's a greenish yellow. It's a penetrating odor. Again, we do not want to be smelling this chemical. It is roughly 2.5 times heavier than air. Again, non-flammable. But one of the properties is it has a high coefficient of expansion. Now, what does this mean? This means that in the cylinders in which liquid chlorine gas comes in, any change in temperature will cause an exponential change in volume. So if you have a cylinder, transporting a cylinder, you want to make sure that you're keeping it temperature controlled, because any change in temperature will potentially cause a rupture in the cylinder. So for example, 1 liter of liquid chlorine can evaporate to produce around 550 liters of chlorine gas. So it expands, it's extreme expansion. Another form of chlorine application is the liquid form. Mostly The most common, sodium hypochlorite. It's an amber color, slightly soluble in water, 1.5 times heavier than water. And sodium hypochlorite is available at around 3 to 19% available chlorine by weight through the manufacturer. One thing that you want to be looking at is that if you're a supply system that receives sodium hypochlorite in bulk in your bulk storage tank, right? Say you receive it at around 16% available chlorine, you want to be running continuous tests because it does degrade with respect to time. So maybe if initially it was 16% over a period of time, you'll observe that it dropped down to 10%. And you want to adjust your feed rate according to that degradation. The next common form is a solid. It is a calcium hypochlorite. It's a white, you can get it in a powder or a tablet. And typical concentrations are between 65 and 70% available chlorine by weight that you'll see and from the manufacturer. You'll see that on your product data sheet. And typically these are observed in smaller systems as a form of chlorine application. So in the chlorine reaction, now we're going to look at the chlorine reaction with water. When chlorine is added to water, it goes through a reaction called hydrolysis. A mixture of hypochlorous acid and hydrochloric acid are formed. So if we look at the equation, this is not a one-way equation. It is a two-way. These reactions are happening back and forth simultaneously. One thing to note is that if you're adding chlorine gas, it lowers the pH of the water. If you're adding a hypochlorite compound, it increases the pH of the water. The reason for this is that with chlorine gas addition, it forms hydrochloric acid, giving the solution a more hydrogen ions in the solution, meaning more acidic, lowering the pH. For the hypochlorite compound, you're increasing the production of the hydroxide ion, which more negative swimming around in that solution will increase the pH, right? So the overall takeaway is that we are producing the disinfectant chemical here as hypochlorous acid, HOCl. To talk about this compound, this is the disinfectant chemical that we're aiming for. And depending on the pH and temperature, the hypochlorous acid will further dissociate to hydrogen ion and the hypochlorite ion. So these are the two main compounds that we want to aim for: hypochlorous acid and hypochlorite ion, right? Those are referred to as the free available chlorine, these concentrations of these. Whether you get one or the other will depend on the pH of the water. And the reason also why the hypochlorous acid is favored is because it is a more powerful disinfectant, usually around 100 times more than the hypochlorite ion. So since they are dependent on pH, we've observed that a pH of around 7.5, you get equal concentrations of both of these compounds. Now let's take a look at the relationship between these compounds and the pH. Here we have on the y-axis to the left the percentage of hypochlorous acid, and the y-axis to the right we see the percentage of the hypochlorite ion. And on the bottom, we see the pHs. We see that as we decrease the pH, we're getting higher concentrations of the hypochlorous acid, right? And as we increase pH, we get higher concentrations of the hypochlorite ion. And as far as temperature, if we increase temperature, like say we're looking at a pH value of 8, right? We get, almost roughly equal amounts of both compounds. And if we increase the temperature, we are decreasing the concentration of hypochlorous acid and increasing the concentration of hypochlorite ion, which is the main relationship with respect to temperature. Anything below a pH of 4, you'll have the hypochlorous acid will start decreasing and chlorine gas will start off-gassing, meaning it'll start evaporating. So we want to operate usually within the range, 7 to 8 pH value for the favoring of the hypochlorous acid. So we talked about what free chlorine is. Free chlorine is the concentrations of both of those compounds, hypochlorous acid, hypochlorite ion, and that added to the combined chlorine will give you a total chlorine, right? Now, what is combined chlorine? Combined chlorine, when ammonia is present in the water or ammonia is added, um, or other organic nitrogen-based compounds, there's a reaction that starts forming and it forms combined chlorine, which is also a form of disinfectant. Let's take a look at this combined form of disinfectant. When we have that ammonia or ammonia-based compounds and it starts reacting with hypochlorous acid, we start getting the formation of the chloramines, monochloramine, dichloramine, and trichloramine. Now, these are, again, as I said, forms of a disinfectant. They are, however, 1/25th less disinfectant power than the hypochlorous acid. But they still can be used, and systems still use these as their main source of disinfectant. Now, the reason or for the chloraminating systems, they are aiming for the production of monochloramine. Now, why choose monochloramine? For these specific reasons. Monochloramine and dichloramine and trichloramine, as we can see, the volatility starts increasing for the dichloramine, trichloramine, which are associated with that smell, that odor, and also that taste. So if you're a chloraminating system, you're aiming for the production of monochloramine, and that is usually accomplished by a chlorine ammonia ratio of 3 or 4, sometimes also, sometimes even slightly higher parts chlorine to 1 part ammonia, right? And usually typically within the range also of 7 to 8 on the pH scale. So when chlorine combines with organic matter in the water, we start getting the disinfection byproducts, primarily trihalomethanes and haloacetic acids, which have a maximum contaminant level. For trihalomethanes, it is 80 parts per billion. For haloacetic acids, it is 60 parts per billion. So now let's take an example. So if we have a water source that has no impurities in the water, it has no demands, it has nothing dissolved in it, just pure water. If we look at the graph, we will see that if we apply chlorine milligrams per liter, we can expect to see that same residual observed, right? If we add 2, 4, 6, we can expect to see 6, 2, 4, 6 as a residual that we're reading. Under the graph, we'll see that concentrations of hypochlorous acid and hypochlorite ion will depend on the pH. The lower the pH, the higher the concentrations of the hypochlorous acid. The higher the pH, the higher the concentrations of the hypochlorite ion. And these are referred to as the free available chlorine or the free available residual. So this is in a perfect world. However, what happens if we apply chlorine to a system that that is high in dissolved minerals and dissolved impurities? We start looking at a graph called the breakpoint chlorination. So if we start adding some of that chlorine to a system, which is often the case, a lot of majority of the systems, or basically all the systems, have some sort of impurities in the water. As we start adding chlorine in this very first region, there is a demand that's rapidly reducing chlorine and using it up, right? With the reactions such as that of hydrogen sulfide, iron, other organic material. It starts consuming that chlorine, and you will not observe a chlorine residual until that chlorine demand area is met. As we push through into zone 1, and we continue pushing and adding chlorine, In zone one, we will start primarily seeing the formation of monochloramines. If you're a chloraminating system, this is the region that you want to operate in, right? 4 parts chlorine to 1 part ammonia, roughly. And in this zone, you also see the formation of trihalomethanes. As we continue applying chlorine and into zone two, in zone two is where you will observe the formation of the dichloramines and trichloramines, which is a zone most associated with taste and odor problems. And in this zone, there's a reaction that happens as you continue applying chlorine between chlorine ammonia and the other compounds in the water that starts reducing the combined chlorine all the way to a point that's referred to as the breakpoint. At this breakpoint, you'll still have a certain amount of combined chlorine residual, right? But after this point, as you continue applying chlorine, you'll start seeing a linear relationship between your chlorine applied and your free available chlorine residual. 85 to 90% of the total chlorine residual will be free available chlorine after this point, right? And of course, depending on the pH of the water, you'll start seeing either hypochlorous acid or hypochlorite ion. A little bit of a recap. Again, zone one, you predominantly form monochloramine and you start getting the formation of trihalomethanes. Zone two, uh, you start seeing that formation of dichloramine, trichloramine associated with taste and odor, right? And again, monochloramine is more effective than the other chloramines. Monochloramine also exhibits a less taste and odor problems, right? And in this zone is where you start reaching that break point with the continuous application of more chlorine. In zone three, you reach the break point, and your chlorine residual increases proportionally with the chlorine applied, right? As you drive off those dichloramines, trichloramines, you start reaching that break point, and after that, you've reduced the combined chlorine to the lowest that it's going to be, and you will start observing free available chlorine after this point. So let's talk a little bit about the basic concept of contact time. So contact time, what is it? Contact time is when you have a concentration and you expose it to water for a certain amount of time is what's referred to as contact time. So EPA specifies combinations of chlorine residual and contact time in minutes that are necessary to properly disinfect a water supply. And you can see some of these graphs, and they are dependent on the type of disinfectant you're using, whether it's free chlorine, whether it's chloramines, etc. They give you these charts as the CT time you must meet for proper disinfection. So the effectiveness of the disinfection is a function of disinfectant strength, um, the contact time or the time that it spends in contact with that disinfectant, the pH as we've seen, um, as we observed and talked about that hypochlorous acid is a better disinfectant, right? That's dependent on pH, the turbidity, and also the temperature. So the disinfection of surface water has been set at a 3 log or 99.9% reduction of Giardia and 4 log 99.99 reduction in viruses, right? And so the residual C multiplied by the contact time T results in a term called CT. And a water system may be required to provide enough contact time to kill bacteria, viruses, or Giardia. And the basic equation is just C multiplied by T is equal to your CT or your contact time, right? Here's an example of one of those graphs that you can obtain from the EPA. So for this specific one, it's a concentration of 2 milligrams per liter of free chlorine, right? And this is the contact time values for a 3 log 99.9% reduction in Giardia. So we can see that we have two factors, pH and temperature, that can affect our CT value. If we hold pH constant, say we hold it at a constant 6, and we increase temperature, we are decreasing the amount of time that the water has to be in contact with the disinfectant to achieve the 3 log 99.9% removal, right? Or reduction, sorry. And this makes sense since at higher temperatures, you're having faster moving particles within the water. It increases the rate of contact with these organisms, right? If we hold temperature constant, say we hold it at 33.8 degrees Fahrenheit, and we increase pH, then you are also increasing that CT time, and inversely, and now actually relationshiply, you're increasing the contact time that must be required to achieve the disinfection, right? And this kind of makes sense too, since again, increased levels of pH, we start seeing hypochlorite ions, weaker disinfectant. At lower levels of pH, we start seeing hypochlorous acid, better better disinfectant power, and therefore a lower CT value. So let's take a look at a quick example on contact time, and so with respect to contact time, this is very basic. There's a lot of steps, including baffling factors and geometry of the water in your plant. But let's take a look at you are required to provide a CT of 100 to protect your water system against Giardia. You have a finished water storage tank at your water plant, and it takes the water 50 minutes to flow through the tank. What chlorine residual C do you have to maintain in order to get that required CT of 100? So again, very, very basic, right? We have our CT value, 100. Oh, sorry, 100. We have our chlorine residual, and we have our contact time. We know that it's 50 minutes to flow through the tank. We can calculate that chlorine residual that we must have in contact with the water for 50 minutes to achieve that 100 CT value, right? And we calculate that by taking 100 divided by 50, 2 milligrams per liter. And again, some factors, and just kind of to recap some of the things that we talked about. So with the pH, as the pH of the water decreases and you're adding chlorine, you get a stronger disinfectant through the formation of the hypochlorous acid. As you add it to a water that has a higher pH, that will produce a weaker disinfectant by the formation of the hypochlorite ion. With ammonia, if you have a water that's high in ammonia, you will have an increased combined chlorine, right? We saw that combined chlorine can only be reduced so much. You will have an increased concentration of combined chlorine, and therefore also an increased chlorine demand to break point. With respect to temperature, the higher the temperature, the faster the reactions will go, and therefore the faster the disinfection if you're observing a water in contact with a certain residual, right? The increased temperature will help in more complete disinfection. As far as time, the higher amount or the greater amount of time or the greater the CT value, the more time will be spent in contact with that water and therefore the more complete disinfection, right? As far as impurities, if you have a source water with a high concentration of these impurities, such as iron, hydrogen sulfide, bacteria, viruses, you will also have an increased chlorine demand, right? And respectively, a less complete disinfection. So jumping a little bit into pumping systems or application systems, and we're just going to touch on this a little bit. There will be other sections in water treatment, in the Water Treatment 1 series that will deal with pumping systems. So for this, we see that there are on-site hypochlorite generating systems that use only salt, water, and electrical power to generate a sodium hypochlorite. There are two main types. There's a high strength and a low strength. A low strength, zero point 0.4 to 0.8 available sodium hypochlorite by weight. High strength, as high as 10 to 15% available sodium hypochlorite by weight. The reason why these are actually starting to increase in popularity is the fact that it's pretty easy to get NSF 60 certified salt, which is what is required. Usually it requires for every 3 kilograms of salt, you produce um, 1 kilogram of chlorine product. And typically using on-site generators, it is about 2/3 of the cost of using liquid bulk sodium hypochlorite. Depending on the system, of course, now with the increase in prices on everything, make sure you weigh the pros and cons of adding a on-site sodium hypochlorite generator. So some of the cons, it produces hydrogen gas, which can be is extremely flammable. And usually another con is the startup cost on these site generators. The startup cost relatively high compared to just getting liquid sodium hypochlorite and a couple of peristaltic pumps, right? And then the biggest drawback is the operation and maintenance. You need food grade salt, highly pure. Any impurities will damage that electrolytic cell. You need temperatures within a certain range, 40 to 80 degrees Fahrenheit, and the water must be softened to the lowest hardness possible, or it could also damage that electrolytic cell. So again, there's pros and cons to these type of systems, and more on feeding systems in other sessions of this water treatment 1 series. So once we've treated a water with chlorine, it's processed. We need methods to determine the residual, whether it be at certain parts of the plant or out in the distribution system. And there are two different methods. There's a titrometric method, which is most commonly used in the lab. You see these in larger water treatment plants, and the colorimetric method. Now, both methods use a color indicator, a DPD chemical. You have your sample, so you take your sample, you add a couple drops or the recommended amount into the sample. It turns it a pinkish red color when in the presence of chlorine, right? And you're titrating this sample with ferrous ammonium sulfate. Ferrous ammonium sulfate will slowly start removing that pinkish reddish color. Once that color is completely gone, you measure the amount of ferrous ammonium sulfate that you consumed, and that is directly proportional to the amount of chlorine residual present in your sample. So again, that's most commonly used in the bigger plants. In the colorimetric method, actual chlorine residual is determined by comparing color development with a known color standard. So let's take a look at some two kits. So the equipment on the left-hand side, that's referred to as a color wheel. And with a color wheel, the way that it works, it can be accurate up to 0 to 4 milligrams per liter of chlorine. You take around a 5 milliliter sample, you add your DPD powder packet. Now again, note that for the DPD powder packet, whether you're testing for free or total, those are two separate packets and two separate waiting times to observe the result, right? You mix it to get a pinkish color. For free chlorine, you want to read the results within 1 minute. For total chlorine, you're adding a completely different packet. You want to wait 3 minutes and read the results within 6 minutes to observe that total chlorine. And again, the results obtained used through the comparison of that color wheel, you start seeing a color and you kind of match that color to the color of your sample, and that'll give you that reading of your free chlorine or total chlorine. And it's not as accurate due to variations in different people will interpret different colors differently. So there is a certain level of error associated with it. And the apparatus, oops, sorry, the apparatus on the right-hand side, that's the pocket colorimeter. We have been recommending that systems use this pocket colorimeter since it is a digital reading, right? Again, the same thing, same concept. You add around 5 milliliters of sample. You add that DPD packet. Whether you're testing for free or total, you're going to wait for free within a minute, for total 3, and read within 6 minutes, right? There are 2 different times. That's very important. And usually a rule of thumb is that your total is going to be around zero point 0.1 times higher than your free. If you start observing that your total chlorine is less than your free chlorine, there's something off. Also, with these pocket colorimeters, you also always want to run a blank with the water you are testing. This acts as kind of like a calibration for the water, right? That you are testing, and then run your samples. Let me take a quick look at the times here. So, in terms of concentration, concentration is a means of expressing the quantity of a given substance contained in a unit amount of another. So for our purposes, it is the amount of chlorine or chemical that is dissolved in a certain amount of water. Typical units are milligrams per liter, also known as, or equivalent to a part per million, as Andrew stated in the previous statement. We can also measure in grains per gallon, but we are what you'll see on the test are going to be milligrams per liter or parts per million, right? The most common uses and expression of a concentration. As far as chlorine forms, again, with chlorine gas, that's 100% available chlorine and typically comes in 150-pound cylinders or 1-ton cylinders. That's also known as bertholite, and chlorine gas. It was weaponized during World War I because, well, when a bomb was dropped in the trenches, since chlorine gas is heavier than air, you start getting that gas seep into those trenches. It would be inhaled by a person, and then the reaction, which would form hypochlorous acid and a hydrochloric acid, you would then drown in your own lungs, right? So that was the application of chlorine in war. For calcium hypochlorite, again, it's a solid. It's usually available 65 to 70% available chlorine by weight. And with sodium hypochlorite, that's 3 to 19% available sodium hypochlorite by weight. It's a liquid. And if we note through the chemical reactions, they are very similar. The overall chemical reaction will still produce that hypochlorous acid and hypochlorite ion, right? We can see these by this equation. They are relatively the same. So one of the things that you want to be observing in the product data sheet, you want to be observing that percentage of available chlorine by weight. If we take a look at this liquid bleach or sodium hypochlorite, that is 12.5% available, sorry, available chlorine. If we look at the very last line under chemical properties, available chlorine by weight, 11.9%. That's the number you want to be using when calculating the concentration of chemical or concentration of chlorine in your calculation problems, right? If we look at calcium hypochlorite or the 68% calcium hypochlorite, and we look at the typical properties, that value, the available chlorine by weight percent, 65%, that's the minimum, so 65% available sodium, available chlorine, right? And that's the number we want to be using when calculating the application doses, right? A couple of important formulas to know. 1 milligram per liter is equal to 1 part per million. An applied applied dose, or a ppm, part per million. That's equal to pounds of chemical, pounds of chlorine, divided by million pounds of water. We have our total chlorine, which is equal to our free chlorine plus our combined chlorine, right? And we have a chlorine demand, which is equal to the applied chlorine minus your residual chlorine, right? It's just some formulas to kind of keep in mind. So let's take a look. Let's take a look at some of the example problems. Let's start with number one. So if we have 15 pounds of chlorine gas were used in 24 hours, during this time, 1 million gallons of water were pumped. Calculate in milligrams per liter the dose of chlorine that is applied, right? So with these problems, and I guarantee that you'll see some of these problems on the test. You want to take it kind of step by step. What you want to do when you start seeing a dosage problem, you want to first convert the water into the correct units, which from the equation, that's represented as million pounds of water. So you see a million gallons or so many liters or gallons per minute. You want to convert that to million pounds of water, as that is what the formula uses, right? So that's step one. So step one, you know that you're using 1 million gallons per day, right? And 1 gallon from the formulation sheet, which you will have on the test. You don't have to memorize. 1 gallon, you arrange that factor, 1 gallon on the bottom, 8.34 pounds on top, right? Gallons cancel. You're still in units of million. So you'll get your answer in million pounds of water per day, 8.34. Step two, we want to solve for the concentration of chlorine, right? So we have the part per million equation, which is equal to pounds of chemical per million pounds of water, right? We have now the two variables that we need, the 15 pounds of chlorine applied in 24 hours, right? And then we also have the converted 8.34 million pounds of water, and the division is 1.8 parts per million or milligrams per liter of chlorine, of pure chlorine, right? And that is our dosage. For problem number two, let's take a look. A certain water supply applies 2 milligrams per liter of chlorine to the distribution system. Using the DPD method, it was determined a free residual of 0.3 milligrams per liter exists throughout the system. What is the chlorine demand? So this goes back to that graph that we talked about. There is that region, that's the chlorine demand. That's the demand that must be met before you start observing a chlorine residual. So with that formula, chlorine demand is equal to applied chlorine minus your residual chlorine, right, that you observed. We have the applied, which is 2 milligrams per liter. That's what you're applying. We have the residual, or what we observed. We can calculate how much chlorine, or the chlorine demand, that is needed, or sorry, that is consuming the chlorine. And that is done by taking your applied chlorine, 2 milligrams per liter, minus 0.3 milligrams per liter, to get a 1.7 milligram per liter chlorine demand, which is what you must meet. And after this, you'll start observing your chlorine residual, right? Let's take a look at this one here. So number three, if a water supply uses 2 milligrams per liter of applied chlorine, how many pounds of chlorine gas are fed in 1 day? 1 day, on this day, the city has pumped 500,000 gallons of water. You're also assuming a 0 chlorine demand. So again, when approaching these problems, you want to, step one, convert all of your flows in million to million gallons per day. That's step one, since a part per million equation has those units of million pounds of water, right? So we're given that. We're given 500,000 gallons of water, right? 500,000, that is half a million, 0.5, right? So 0.5 million gallons per day are being processed. We take that conversion factor, We take that conversion factor that we obtained from the formulation sheet, right? We rearrange it accordingly for the units to cancel out. We have gallons cancel out, and we're left in units of million pounds, which is exactly what we want, right, to plug into our part per billion equation to give us a result of 4.17 million pounds of water. For step 2, it asks how many pounds of chlorine gas are fed in 1 day. So we have our million pounds of water. We also have our concentration of applied chlorine, 2 milligrams per liter, or 2 ppm. So we rearrange the equation accordingly. Pounds of chemical is equal to part per million multiplied by million pounds of water, right? We calculated both. 2 ppm multiplied by 4.17 million pounds of water will give us 8.34 pounds of chlorine. So 8.34 pounds of pure chlorine will give us this it is this residual of 2 milligrams per liter of applied chlorine. So let's take a look at number 4. And number 4, let's work out together. So number 4 reads, a water system processes 2.5 million gallons of water a day and applies a 2 milligram per liter of chlorine, right? That's the dosage. If calcium hypochlorite is used, 65% by weight available chlorine as a disinfectant, how many pounds of powder are used? So again, when approaching these, what do we want to do first? We want to convert any flow into million pounds of water, since that is what the part per million equation will use, right? So we're given in the problem statement that it uses 2.5 million gallons of water, right? So we have 2.5 million gallons per day. We know that from our formulation sheet, we want to convert that to pounds or million pounds. So what are we going to use? We're going to use 1 gallon of water is equal to 8.34 pounds from our conversion factor sheet. And this will be given to everyone on the exam, right? And it contains a variety of factors that you'll use. So we want to rearrange that in the correct way. So 1 gallon on the bottom is equal to 8.34 pounds on top, right? We have our gallons cancel out. We do a quick units check, right? We're left with 2.5, and that's million gallons times by 8.34 pounds, right? We do that. We have 20.85 million pounds of water, right? So we got our units. We want million pounds of water. The second, we want to find, we want to solve for the pounds of chemical or the pounds of chlorine that are being used, right, to achieve that 2 part per million chlorine residual and for that water, right? So we rearrange the part per million equation. Pounds of chlorine is equal to a part per million multiplied by the million pounds of water. Well, we're given the part per million in the problem statement, that is 2 ppm, right? We just calculated the million pounds of water. That is 20.85 million pounds of water to give us 41.7 pounds of chlorine. So 41.7 pounds of chlorine is what's needed to achieve that chlorine dosage of 2 milligrams per liter. But we are given the fact that we're using um, calcium hypochlorite, we have to take it an extra step since the problem statement is asking how many pounds of the powder do we use, right? So we know that it's 65% pure, right? So 65% of a certain amount of weight will be pure pounds of chlorine. We have the pure pounds of chlorine that we need to achieve that residual. That's 41.7, right? We know that 65%, right? And 65% is represented as a decimal form, 65. When we multiply that by the total pounds of the powder, right? Setting it up this way, it just basically reverts to a basic percentage calculation. We know that 65% of a certain amount of powder will give us that purity, the pure chlorine of 41.7. So we rearrange the equation and pounds of powder is equal to 41.7 pounds of chlorine divided by 0.65. So this gives us 64.15 pounds of powder. This is how much powder you need to achieve that 41.7 pounds of chlorine that will achieve the 2 part per million application dose, right? So 64.15 pounds of powder is what we need. Let's take a look at example 5. So example 5 states a water system processes 2 million gallons of water per day and applies 2.5 milligrams per liter of chlorine. If sodium hypochlorite, 15% available by weight, is used as a disinfectant, how many gallons are used in one day? Assume 1 gallon of sodium hypochlorite weighs roughly 10.4 pounds. So they're giving us a density, they're giving us the dosage, and the water that's processed, and the percent available by weight. So again, we take this step by step. You always want to convert how much water you have. That's 2.0 million gallons, right? That's per day. You use that conversion factor, 1 gallon, 8.34 pounds, right? Oh, sorry. 2 million gallons per day, 1 gallon, 8.34 pounds, right? We're converting to million pounds of water, 16.68 million pounds of water. That's what we need. The next step, as before, we want to find the pounds of chlorine that we need to achieve that. We're given the part per million, 2.5 ppm, right? Multiplied by 16.68 million pounds to give us 41.7 pounds of chlorine, right? Now that extra step, we see that this is the same number that we obtained for the previous problem, but now we're going to get a different pounds of solution because of the purity. We're given that it's 15% available chlorine by weight, right? So we know that this 41.7 pounds of chlorine, that's going to be equal to 15%, or the available chlorine by weight, multiplied by the total pounds of solution, right? And that's what we're solving for. We're solving for the pounds of solution to eventually get the gallons for every day. So we rearrange the equation, or pounds of solution. That's equal to 41.7 pounds of chlorine divided by 0.15, right? That gives us 278 pounds of solution. So we have our pounds of solution, and we're given in the problem statement that our density is 10.4 pounds of solution. That's how much it weighs for every gallon of that solution. So we take that 278 pounds of solution, right? We know that 10.4 pounds of that solution in 1 gallon, which allows us to calculate. And again, we take 278 divided by 10.4, and 26.73 gallons of solution per day. So with liquid sodium hypochlorite, again, to get that, you're using different concentrations of purity, which will give you a different pounds of solution or different pounds, and you can relate that to calculate how many gallons you'll need for that day to achieve that dosage.